It's a pleasure to have Colin Fourel from Strasbourg and not Lyon as advertised on the website, who will talk about flow categories as exit path categories.
Okay, thanks for the introduction and thank you very much for the invitation. So what I want to do in this talk is give you a new perspective on flow categories of Morse functions, which involve the notion of quantified spaces and exit path infinity categories. So we start by recalling how flow categories show up in Morse theory. Let me take X a smooth closed manifold of dimension n. And then X, I take a Morse function. And I pick psi, negative gradient-like vector field for F. So when I say gradient-like, I am assuming that near each critical point in a Morse chart, psi is really the opposite of the gradient. And I assume that it satisfies the Smale's transversality. And okay, and I will denote by C the set of critical points of F. And for a critical point X, I denote like this the Morse index of X. This is the dimension of the negative subspace of the Hessian at X. So out of this datum, can define a topological category, which is called the flow category of this datum. So definition of this is the following. So the flow category of X, F, and Xi. This is a topological category. And then I denote by curly M. Its objects are the critical points of F. And between two critical points, X and Y, the space of morphism is the space of broken trajectories of Xi. So possibly broken trajectories of Xi between X and Y. So when I say broken, I mean that I'm considering trajectories that link X and Y directly, but I also allow for a concatenation of trajectories that link intermediary critical points between X and Y. And I said this is a topological category, so I have to put a topology on MXY. And this is done by using the fact that every trajectory has a natural parameterization by the interval of values of F between X and Y. So I can inject MXY into this set, and I put the compact open topology induced on MXY from this. And here, the reason why I have I have Y and then X because I took a negative pseudo gradient. So this induces topology on MXY. So let me draw an example. So as an example, I will take x equals S2, the two sphere, and I look at it as embedded in the three-dimensional space like this. And f will be the height function with respect to the vertical axis. And for psi, I will just take the opposite of the Euclidean gradient, f. So there are four critical points, x, y, z, and t. And psi looks like this. So let me describe a few of the morphism spaces. So between x and z, there is just one trajectory, which is this one. So mxz is just a point. Then between z and t, there are exactly two trajectories, one that goes in the front of the picture and one that goes in the back. And so mzt is a disjunction of 2 points. And so what about mxt? Between x and t, there are exactly two broken trajectories, which corresponds to the concatenation of the one from x to z, and then the two from z to t. And then between these, there is a one parameter family of unbroken trajectories that goes around picture like this. So in the end, mxt is a closed interval. Okay, so that's for the example. And that illustrates the general result, which is the following for any any x, f, and psi between two given critical points, x and y. So mxz has a structure of smooth manifolds of compact smooth manifold with corners. That the interior is the set of unbroken trajectories. That the interior of mxz is the set of unbroken trajectories. So flow categories are also a fundamental object in symplectic topology, because in some cases the compactified moduli spaces of solutions to Fleur's equation can be organized in such an object. So what I want to do in this talk is to really see M as a topological category and observe that in this way it defines an infinity category. So I want to see M as an infinity category. So now I need to tell you a little bit what an infinity category is. So I will give a very vague definition. So an infinity category is a generalization of the notion of a category in which the morphisms are spaces. So let me just say that an infinity category is a category with spaces of morphisms. And here, when I say space, I really mean space of two homotopy. I mean topological space of two homotopy. Means the topological space of two homotopy equivalents. So this is a very vague definition at the moment. There are many very good reasons to consider this kind of object, some of which will appear later in the talk. So let me not say more about this definition for the moment. One way of precisely defining the theory of infinity categories is to rely on a specific model. And one model is provided by topological categories. Every topological category defines an infinity category. And so the theory of infinity categories is related to the classical homotopy theory of topological spaces by a functor called the geometric realization functor. So there is a functor. Denote like this from infinity categories to spaces called geometric realization, and the relation with the Morse theoretical setting that I just explained is the following theorem of Cohen, Jones, and Segal. Cohen, Jones, Segal in 1999. That the geometric realization of the flow category is a homotopy equivalent to the manifold X. So now we have the following situation. Suppose I take a different choice of Morse Smale pair on X, F prime, psi prime, Morse Smale on X. Then I have the following picture at the category of infinity categories, which goes to the category of spaces by the geometric realization. And let me denote by M prime the flow category associated to this other choice of Morse Smale pair. M prime the flow category. Then here I have two infinity categories, M and M prime, that are both mapped to the same objects in spaces, which is F. But I want to observe that in general, M and N prime are not equivalent above. So in general, M is not equivalent to M prime in a category of infinity categories. Let me give you an example. So as an example, I still take X equals S2, but I just embed it in R3 the usual way. And I take the height function F prime on it. And psi prime is again the opposite of Euclidean gradient. So now there are two critical points, X and Y. And between X and Y, there is a circle of gradient trajectories like this. MXY, M prime XY, sorry, is S1. But none of the spaces of morphism of M have the homotopy type of S1. So M and N prime are not equivalent infinity categories. So somehow M is a finer object than the homotopy type of X itself. And the question I want to address is, does M as an infinity category reflect some additional structure on X? Does M reflect additional structure on X? And the answer to this question involves the notion of stratification. So out of F and Xi, you can define a partition of X as a union of disjoint submanifolds as follows. So for every critical point of F, I define big X lower or small x to be the subset of those points in X such that the flow line of Xi that passes through the point P tends to X at infinity. And this is called the ascending manifold of X. Small x. And as every flow line of Xi tends to a critical point at infinity, this defines a partition of X as a disjoint union. So X is a disjoint union over all the critical points of the corresponding ascending manifold. So this is a stratification, which you can just think for the moment of as a partition space. And to handle this stratification, it will be convenient to introduce a partial order on C. So, let me declare that for all pair of critical points, X is smaller or equal to Y if and only if MXY is non-empty, which is also equivalent to the fact that the ascending manifold of X is included in the closure of the ascending manifold of Y. This is sometimes called the Smale ordering, I think. So let me draw for you this stratification in the preceding example. So I take again my first example. So what are the ascending manifolds of the two local maxima when they are reduced to a point? So this is ascending manifold of X, ascending manifold of Y. But the only trajectory that tends to this point is the constant one. Then what about ascending manifold of Z? Well, you can see that all the points that flow to Z at infinity are on this part. This is X, Z. And then all the rest flows to the minimum. This is XT, right? And the partial order on C is as follows. So X is smaller than Z. Y is smaller than Z, and Z is smaller than G. It turns out that this stratification enjoys a nice regularity properties. So, that's a theorem that is due to Nicolescu in 2010, I think. Which is the following. Said that if I fix x and f, then psi, if I just assume that psi is a negative gradient-like vector field, then psi is Smale. Smale. If and only if the two following conditions are satisfied. First, for all k greater or equal to 0, the union of ascending manifold of dimension, the union of the critical points of index greater or equal to k, the ascending manifold of x is closed in x, and a regularity condition on the stratification called the Whitney regularity condition is that for all k greater than L between 0 and n, so the pair formed by the union over the critical points of index k, the ascending manifold of x, and the union over the critical points of index L of the ascending manifold of x satisfies the Whitney regularity condition. So I think there are usually two Whitney regularity conditions. Here I'm talking about the strongest of the two. So I will not define exactly what this condition is, but let me still tell you a little bit about Whitney regularity. So Whitney regularity. So the setting is the following. Let me take N, a smooth manifold. And inside N, X and X prime, let me code them Y and Y prime. I already used X, Y and Y prime, two disjoint submanifolds. And although they are disjoint, I'm assuming that Y is included in the closure of Y prime. So maybe the picture looks like this. We take N to be R3. And inside R3, I have X, yeah. Oh, sorry, Y. And above Y, I have Y prime, like this. Y prime. And I will take a T in N, a tubular neighborhood of Y. So something that looks like this on the picture. So T as a tubular neighborhood, it is equipped with a radius map to the positive real numbers. Radius map. And with a projection map to X. And also, if I choose alpha a smooth function from X to the strictly positive real numbers, I will denote by S alpha the set of those points in T which are at distance alpha from X, so for which alpha of phi of V equals the radius of V. So this is some kind of circle bundle above. Sorry, here it's really Y. So this is some kind of circle bundle above Y, except that I allow the radius to vary along Y because essentially because I'm not assuming Y to be compact. And so what the Whitney regularity condition says is that so property so if the pair formed by those two manifolds Y and Y prime satisfies Whitney regularity, and then there exists such an alpha such that for all alpha prime smaller than alpha, the intersection between S alpha and Y prime does not depend. The intersection between S alpha prime and Y prime does not depend on alpha prime. So what does this I will just give a name to this. So it is called the link between Y and Y prime, and it is denoted link by Y prime like this. So on this picture, assume that the boundary of this tubular neighborhood I draw is S alpha prime. So here I have alpha prime as a radius. Then the link is this red part, the intersection of the boundary with Y prime. Okay. And moreover, there is another property which is satisfied, which is that the link, so the restriction of the projection pi in the link to Y is a fiber bundle. So geometrically, what does this mean? Well, in particular, it's a fiber bundle. So in particular, the diffeomorphism type of the fibers does not depend as we move on Y. So if I fix a point in Y and I look at the sphere above it, and I look at the intersection of this sphere with Y prime, here is just a point, and I move on the base, then this intersection won't change. Okay, it's just a point. So this really is what the Whitney condition means. So now, by this theorem, in the Morse setting, we have Whitney stratification. So you can wonder what these links are. That's what I'm going to describe. So what are the links in Morse theory?
So,
Yes.
when you see that the diffeomorphism type of S alpha prime intersect Y prime does not depend on alpha prime.
Yeah.
Do you require some extra control on how the diffeomorphisms go?
Well, if I have two alpha prime and alpha second, I can have a homotopy between them because they're the fixed values in R plus strictly positive real numbers, and it is enough to guarantee that I have a diffeomorphism between the intersection.
I'm just kind of worried that alpha prime goes to zero, or kind of things are still diffeomorphic, but it kind of becomes complicated. Becomes not so controlled. I don't know.
Yeah, I'm just claiming that they are diffeomorphic. So in Morse theory, let's take X and Y, X smaller than Y, two critical points. So in that case, we know that, so then X is inside the closure of XY, and the pair XY is the Whitney regular. By this theorem. So what is the link between these two strata? So as I said earlier, there is a fiber bundle. The link projects to the first stratum. This is the fiber bundle. And let me denote by Fx the fiber over X. But in our cases, the strata are contractible. So since XX is contractible, the inclusion of the fiber into the total space is a homotopy equivalence. I is a homotopy equivalence. And I'm only interested in the links up to homotopy equivalence, so it will suffice for me to describe this fiber. So let me do that. And to do that, I will work in a Morse chart around X. So let's consider a Morse chart around X, in which psi is really the opposite of the Euclidean gradient. So around X, the picture looks like this. So here I have X. Here I have the negative subspace of the Hessian. Here I have the positive one. And the flow goes like this. So to describe the link, I first need to pick some tubular neighborhood. And what I will do, I will just do something like this. Take the points that are at most some given distance of h plus. So this is my tubular neighborhood. And the projection is just the orthogonal projection on h plus. So pi is the projection like this. And so I want to describe the f of x. So first, I will look at the preimage of x by pi. This is just h minus. Okay. Then, since I'm interested in the link between xx and xy, let me look at the intersection of pi minus 1 of x and xy. Sorry. Yeah, and I will also look only at the points that are in the tubular neighborhood. So the points in H minus, if I look at the flow lines that pass through it, it flows to x at minus infinity. And I also take the points in xy, so I also look at the points which flow to y at plus infinity. So these are the points in T which lie on the flow line from x to y. And then to fully describe f of x, I'm looking at this intersection. And I just look at what is on the boundary of the tubular neighborhood. And in the end, intersecting with the boundary just amounts to taking the intersection with a sublevel set of f. I'm taking the intersection of the set of points which are on the trajectory from x to y with a sublevel set, which is the set of unparametrized trajectories from and unbroken trajectories from x to y. So this is the interior of xy. So the conclusion is that the interior of mxy is homotopy equivalent to the link between the two ascending manifolds. But also recall that mxy is the the interior of mxy maps to mxy itself. But this is the inclusion of the interior of a smooth compact manifold with corners. So this is a homotopy equivalence. So what we see here is that M is an infinity category whose spaces are linked spaces. So in the case when we have two strata, the link between them tells us about how they fit together, how they piece together. But if we have more than two strata, we have several link spaces, and we can wonder how they fit together. And M, as an infinity category, provides a way to compose link elements. So M, as an infinity category, has link spaces as morphisms. Link spaces as morphism spaces. And there is, so now what I want to talk about is another construction of infinity category in which these link spaces show up as morphism spaces. And it follows from more homotopy theoretical description of these link spaces, which involve the notion of exit path. So let me define this. So what is an exit path between two strata? An exit path between the stratum of X and the stratum of Y. This is a path in X, gamma, in X, such that it starts in the X stratum, so gamma 0 is in the first stratum, and then it exits in the second one and stays in it at all times. So gamma T is in the second stratum for all strictly positive time. We draw what it looks like. Assume this is the first stratum. This is the second one. And an exit path starts here and then exits above. And here I draw the case when the two strata are different, but it can be that they are both the same, in which case an exit path is just a path that says in one stratum at all time. And the connection with what I said earlier is the following proposition, that there is a weak homotopy equivalence that goes from the link space between the two strata and what I denote by exit between the two strata. Which is just the space of exit path with the compact open topology.
Here, gamma can in principle come back to x of x. Or
No, gamma can't.
ah,
Gamma is in xy at all positive time.
yes. But if xy contains x of x.
But the strata are all disjoint.
Ah, they're all disjoint.
X of x is in the closure of x of y, but it's disjoint from it. So what this proposition implies is that the notion of exit path, it allows to give us access to these link spaces even in setting when we have stratifications which are defined in a purely topological way. For example, no smooth structure. Exit paths are defined for very general notion which don't require any smoothness. And so they are a fundamental object in stratified homotopy theory. And so using this description of the link spaces, we have the following theorem, which is a combination of results of Tom and so 69 and Lurie around 2010. So don't know exactly.
So when you say it's defined in general for topological paths, topological space, you need a notion of continuous distance. No, you don't. If you have discrete distance, all your radius map and things, right? Like if you have like the general, how does it still work?
You mean the notion of exit path?
Yeah.
Well, if I have, I mean, I can, if I have, if I have, for example, yeah, if I have a topological space decomposed as a disjoint union of for example, if I have a closed subset and its complement, so I see that as a stratified space with two strata, the notion of exit path is well defined. Just take the path that starts on the closed subspace and then.
Yeah, sure. I was worried about the tubular neighborhood and the distortion of Whitney regularity that you can.
You mean to prove that we have a homotopy equivalence? Well, this is true for any Whitney regular pair. So the theorem is the following. So there exists an infinity category that is denoted phi infinity of x comma c. And here c is here to denote the fact that x is stratified by the coset of critical points called exit path infinity category. That satisfies the following property. So the points are, or the objects are the points of x. And the space of morphisms between 2 points is the space of exit path between these. Space of morphisms between P and Q is the space of exit path between P and Q.
C is the bigger category. What is
The C is the the poset of critical points. So here it's just, this notation is supposed to denote the fact that X is stratified by C. So just a word about the people here. So Lurie proved this theorem for a class of stratified spaces which satisfies some regularity condition, which is expressed in purely topological terms. So it's called the conicality regularity condition. And the fact that Whitney stratified spaces satisfy this condition is the part that is due to dots. So a theorem that I proved that actually is in the Morse setting, these two infinity categories are equivalent. So M and the exit path infinity category of Lurie are equivalent infinity categories. So in the remaining time that I have, let me tell you a little bit about the proof. Outline of the proof. So the challenge to construct the exit path infinity category is that we want an infinity category whose morphisms are exit path. But you see that exit paths don't compose on the nose B, because if I have two exit paths which visit both two strata, then their composition visits three strata, so it's not an exit path. So one has to find a way to define composition, and this relies on another model for infinity categories, other than that of topological categories, which is that of simplicial sets. So infinity categories can be modeled by simplicial sets. And in this model, the exit path infinity category is a subsimplicial set of the singular simplicial set of X, so a stratified singular simplicial set. And how is it defined? Well, an n simplex of this simplicial set, the singular simplex in X, which is stratified for some increasing sequence of n critical points. So let me, what I mean here is that for every increasing sequence of, n plus one critical points, there's a stratification of the standard n simplex, and I ask for sigma to be compatible with this stratification. So what does the stratification looks like? So for n equals 1, if I have a sequence of two critical points like this, then the stratification of delta 1 is the following. So 0 is in the orange stratum and all the rest is in the red stratum. So this is delta 1. For n equals 2, if I have an increasing sequence of three critical points, x0, x1, and x2, there's an associated stratification of delta 2 which looks like this. So the first vertex is in the first stratum, then the rest of the base is in the second stratum, and then all the rest is in the new stratum. And there is a definition for every n. So we look at simplices, singular simplices in X that respect this stratification. And now I want to compare M, the flow category, with this simplicial set. But again, I have two infinity categories defined in two different models, so I need to relate the two different models, and that is done using to M, I can associate a simplicial set called the homotopy coherent nerve of M. This is the simplicial set, and I want to compare it with the stratified singular simplicial set. So let me describe for you the simplices of this simplicial set. So for n equals 0, the simplices of the nerve of M are just a set of critical points. So this is a subset of X. So to each object of this simplicial set, I can associate a point in X. For n equals 1, one simplex, it's the same as two critical points, x0 and x1, and a morphism between them, gamma 0. So sorry, yeah. What I mean here is that one simplex of the nerve is the same as this day2. But now, as I said at the beginning of the talk, when I have a trajectory here, gamma 0, I can parameterize it by the interval of values of f between x0 and x1. So this is a parameterization of gamma 0, and I denote it f sigma. So this is a path in X the path in X that starts at x0, that ends at x1, but in general, nothing prevents gamma 0 to be a broken trajectory. So it can happen that it visits an intermediary stratum between x0 and x1. This is in the case when it's broken. But you see that this is not an exit path because an exit path visits only two strata. So what I do, they define a subset of the one simplices called S1, and S1 is formed by those one simplices such that gamma 0 is unbroken. So in that case, really, F sigma starts in the yellow stratum and then spends the rest of the time in the red stratum. In that case, F sigma is an exit path. So to finish, let me just briefly explain how the rest of the proof goes. So for every n, I define a subset of the n simplices of the coherent nerve, Sn, which essentially is a generalization of this condition, which is there to ensure that to a n-simplex, I can associate a stratified n-simplex of X. And then I have a zigzag of morphisms of simplicial set, S, which goes to the coherent nerve, and which also goes to the stratified singular simplicial set. I have two morphisms of simplicial sets. Let me finish. So these are two morphisms of simplicial sets. And what I prove is that S is an infinity category. And these are both equivalents. So I1 is an equivalence. And the reason is that at the level of morphism spaces, it induces homotopy equivalence. And the morphism, these maps of morphism space is really the inclusion of the interior of the morphism space of MXY into it. So this is the equivalence. And I2 is an equivalence. And here, the reason is that also it induces a homotopy equivalence at the level of spaces of morphisms. And here, this is the inclusion of the set of broken trajectories, the space of broken trajectories, into the space of exit path, which is a homotopy equivalence. So yeah, that's the rough idea of the proof. And let me stop here.
Questions? I have a general question. So this is mostly in the Morse setup.
Yeah.
Completely biased. What about the Fleur setup? Is it reachable, or where are like the biggest problem in pushing this?
Well, if I have a flow category which arises from a Fleur setup, M, and I have two objects, X, Y, and M. I can say that X is smaller than Y if and only if MXY is non-empty. That defines a partial order on the set of objects, and that makes M as an infinity category stratified in some sense. So when I take the geometric realization, it's also stratified. So the geometric realization of M is a stratified space that is related to M, but maybe that's not such a satisfactory answer because it's not a space that arises from a geometric setting in the first place. So whether, like how to exhibit such a space, I don't really know. Because if I want to exhibit a stratified space, in the first place, I need to have a space and like also how to exhibit such a space before defining stratification, I don't really know.
More questions? If not, that thanks Colin again.